Welcome into the class of number theory, and today we will discuss the basic properties of divisibility. What is divisibility? What are its properties? What is the division algorithm? What are prime numbers, composite numbers, etc. So this is our lecture on divisibility today, the basic concepts of divisibility. So first of all, you must understand divisibility. What is divisibility? An integer a is said to be divisible by another integer b, which must not be 0 if there exists some k in the set of integers such that a is equal to b times k. And if a is divisible by b, then we denote it as b divides a, and we read it as b divides a. So this is b divides a. That means b is divisible by a. Here I am saying a is divisible by b. So I must change the notation here that a is divisible by b. B divides a. B divides a means a is divisible by b. So b divides a means a is divisible by b. This is the basic concept that what is divisibility. And here one thing is to be noted that b, the divisor, must not be equal to 0. For example, your 35 is divisible by 7. Why? Because there exists integer 5 such that your 35 is equal to bk. B is 7, so 7 times 5. This 5 is your k. That I said that exists some integer satisfying this property. So 35 is equal to 7 into 5. So 7 divides 35. In fact, every factor of a natural number divides the natural number. 7 divides 35 as well as 5 divides 35, because in that case 7 will become your k. So from here you can see that your 7 divides 35. Similarly, you can say your 5 divides 35. But if I say that whether 6 divides 35 or not, the answer will be no, because there does not exist any integer k such that 6k is equal to 35. I can't find such an integer k satisfying 6k is equal to 35. So 6 does not divide 35, and we denote it as 6 does not divide 35. So this is the sign, this is the symbol for does not divide, and this is the symbol for divides. So 7 divides 35, 5 divides 35, 6 does not divide 35. So these are the basic symbols we are going to use in the chapter of divisibility. And the very first definition after divisibility is the definition of greatest common divisor. What is the greatest common divisor? GCD. So the definition of greatest common divisor. So definition is very easy. Let a and b be any two integers, then d belonging to z. That means your greatest common divisor is also is an integer. So then d belonging to the set of integers is said to be greatest common divisor of a and b if two conditions are satisfied. First condition is that d divides a and d divides b. and it justifies the word common. That means D is a common divisor of A and B. D divides A, D divides B. So D is a common divisor of A and B. So it justifies the word common in the greatest common divisor. And second condition is that if D dash is some other integer which also divides A as well as B, then D dash divides D also. So that means if D dash is a divisor of D and D dash is a divisor of B, then D dash divides B. That means D dash is either equal to D or D dash is an integer which is smaller than D, and it justifies the word greatest here because D is the greatest common divisor. If there is some other common divisor, D dash, then it must be smaller than D and it must also be a divisor of D. So this is the definition of greatest common divisor, and we normally denote the greatest common divisor of A and B as A, B within the round brackets. So D is equal to AB. That means D is greatest common divisor of A and B. So this is the symbol, and here you have the definition of greatest common divisor. Then there are some basic facts about divisibility, about divisors. One of the basic concepts is the concept of prime numbers and composite numbers. Prime numbers are those numbers which have only two divisors, 1 and the number itself. For example, 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31 and so on. Infinitely many. There are infinitely many prime numbers. You take any one of these, suppose 13. Then which are the divisors of 13? There are only two divisors, 1 and the 13 itself. So 1 divides 13 and 13 divides 13. There is no other number, there is no other integer which divides 13. So 13 is a prime number because it has only two divisors in the form of 1 and 13 itself. So any number, any integer which is having only two divisors, 1 and the number itself, is called a prime number. And all the other numbers which are not prime will be called composite. So these are prime numbers and the complementary set. That means the numbers which are not prime, they will be called composite numbers. They will be composite numbers. So which numbers are not here? Look at 2 is here, 3 is here, 4 is not here, so 4 is composite. 5 is here, 6 is not here, so 6 is composite. 7 is here, 8, 9, 10 are composite, and so on. One thing is to be noted that 1 is considered to be neither prime nor composite. It is neither a prime number nor a composite number. So if you are being asked a question which is the smallest positive composite number or composite integer, then your answer must be 4, not 1, because 1 is neither prime nor composite. And the smallest prime number is 2, even if it is an even number, and it's the only even prime number. There is no prime number afterwards 2 which is even. So 2 is the only even prime number. So these are the basic definitions of prime numbers and composite numbers. And then we will move on to little bit, very easy you can say, 2 or 3 properties of divisibility. The first one is that A is divisible by A for every A in the set of integers. Every integer is divisible by itself. Why? Because there exists integer 1 such that this A is equal to 1 times this A. So it shows that every integer is divisible by itself. So that means the property is reflexive property if you want to say in that form. So it is a reflexive property, but it is not, you can say, symmetric, because if A divides B, it does not mean that B also divides A. For example, 2 divides 4, but 4 does not divide A. So if A is divisible by B, then B is not divisible by A. So this property is not symmetric. Yes, the property is transitive, because if A divides B and B divides C, then A divides C also. The reason behind is very easy. Here A divides B. That means there exists integer k1, you can say, such that your B is k1 times A. And B divides C, so there exists k2, another integer, such that your C is k2 times B. And here you substitute the value of B from here. The value of B is k1A. Put it here. What you are going to get is that C is equal to k2 times k1A, and you can write it as C is equal to k2 k1 times A. K1 is an integer, k2 is an integer, and we know that product of two integers is also an integer. So k2 k1 is also an integer. You can rename it as k. So C is equal to ka, where your k is k2 k1, or you can say k1 k2. So C is equal to ka. So that means there exists an integer k such that C is equal to ka, and this means that A divides C. So if A divides B and B divides C, then A divides C. So the property is transitive property. Another thing is that if an integer divides two integers, then it also divides their GCD. That means what I want to say, if n divides A and n divides B, then n also divides GCD of A and B. And the proof is again very easy. So here n divides, let D be the GCD of A and B. Let D be the GCD of A and B, and we know that by the definition of greatest common divisor, then D divides A and D divides B. Now, D divides A, D divides B means A is equal to dk1 and B is equal to dk2. There will be some integers k1 and k2 satisfying this property. Also n divides A. So n divides A and n divides B. We know that from the definition of the second part of the greatest common divisor, if D is the greatest common divisor of A and B, and if D dash divides A and D dash divides B, then D dash also divides D. So if n divides A and n divides B, then n is the common divisor of A and B. N is a common divisor, and D is greatest common divisor. So n must divide D. That means n must divide D. D is GCD of A and B. In fact, in the proof, this step was not necessary. You can omit, you can delete, you can leave this part. You can directly move from here to here. Since n is a common divisor of A and B, n must divide the greatest common divisor of A and B by the definition of greatest common divisor. There is another very interesting property, that if P is a prime number and P divides the product AB, then P must divide either A or B. So I am writing here, if P is prime and P divides AB, then P divides A or P divides B. The proof is once again very easy. It is given to us that P divides AB. It is given to us. We have to prove that either P divides A or P divides B. If P divides A, then we are through. because nothing to prove, because we have to prove that either P divides A or P divides B. So if P divides A, we have nothing to prove, the theorem is proved. So we take the other case, that means P does not divide A. Let P does not divide A. Now P does not divide A and P is a prime number. P is a prime number. We know that prime number has only two divisors, 1 and the P itself. So P does not divide A means GCD of P and A is 1. GCD of P and A is 1. That is very much clear because P is a prime number and P does not divide A. So P and A has GCD V1, and look at PB and AB. Suppose PB and AB, their greatest common divisor is D. Now P divides PB, P divides PB, and P divides AB also. P divides AB, P divides PB also. So that means P divides D. So this means P divides D. So P divides GCD of PB and AB. Now look at GCD of P and A is 1. They are not having any common factor. P is not dividing A. P is not dividing A. P is dividing D. P is dividing D, and P is dividing D means P divides both of these. P divides PB and P divides AB. P divides D. So P divides D means P divides GCD of these two, PB and AB. In PB there is B, in AB there is B, so B can be taken out. So this means P divides B times GCD of P and A. But what is GCD of P and A? GCD of P and A is 1. So this means P divides B times 1. So this means P divides P. That means if your P does not divide A, then it must divide B. So that is proved that either P divides A, and if P does not divide A, then P divides B. So P divides A or P divides B. So this is a very important result, will be used again and again in the number theory, that if P is a prime number and it divides the product AB, then P divides A or P divides B. There is another very easy concept, that if C divides A and C divides B, then C divides any linear combination MA plus NB of A and B. If C divides two numbers, then C divides each and every linear combination of these two numbers. Proof is easy. C divides A, so that means there exists K1 and there exists K2, both are integers, such that from here you will get A is equal to CK1, and from here you will get B is equal to CK2. Now look at your number MA plus NB and substitute the values of A and B. So value of A is CK1, so it is M CK1 plus N CK2. And now you can take out C common. So it is MK1 plus NK2. Now M is an integer, K1 is an integer, N is an integer, K2 is an integer. So that means this whole is an integer. So you can rename it as K. So suppose I am writing it as CK, where K is an integer. Now what you are having here is that MA plus NB is C times some integer, and it directly means that C divides MA plus NB. So if C divides A and C divides B, then C divides each and every linear combination of A and B. And then we are moving on to division algorithm. What is division algorithm? Division algorithm says that if A and B are two integers with B positive integer, then there exist unique integers Q and R such that A is equal to BQ plus R, where R is greater than or equal to 0 but is strictly less than B, and Q and R are unique integers. So we'll prove this term. This is the division algorithm. The division algorithm. So we are going to prove it. If A, B are integers with B greater than 0, then there exists unique integers Q and R such that A is equal to BQ plus R with R greater than or equal to 0 but strictly less than B. Now we are moving on to the proof. For the proof, consider this set. Consider the set A minus BK type of numbers such that A minus BK is greater than or equal to 0. And this set is non-empty. Why this set is non-empty? Why this set is non-empty? Because you want to have some number here. And you want A minus BK to be greater than or equal to 0. That means you want A to be greater than or equal to BK. Or you can say you want K to be less than or equal to A upon B. And this is always possible. A upon B, whatever A upon B is, there are infinitely many integers K which are less than or equal to A upon B. So this set will be non-empty, and in fact it will be an infinite set. It will be an infinite set. So this set is having a lower bound because every member of this set is greater than or equal to 0. And we know that if a set is bounded below, then it must have a greatest lower bound, or you can say the least member of this set. So whatever the least member of this set is, name it as R. Let R be the least, or you can say the smallest integer belonging to this set S. Since R is a member of the set S, R must also be of the type A minus BK. Maybe for some Q instead of this K. So R is of the type A minus BQ. R is of the type A minus BQ, or you can say your A is equal to BQ plus R. So we are approaching towards the proof. A is equal to BQ plus R, what we wanted is already there. Now what else we want to prove? That this R is greater than or equal to 0 and is strictly less than B. R is greater than or equal to 0 is by definition, because R we have taken from the set S, and the set S contains the members which are greater than or equal to 0. So R must also be greater than or equal to 0. So this part is already covered. A can be expressed as BQ plus R is covered. R is greater than or equal to 0 is also covered. Now what is left is to be proved that R is less than B. Suppose if possible your R is greater than or equal to B. What will happen? If your R is greater than or equal to B, then R minus B is greater than or equal to 0. And what is the value of R? What is the value of R? Value of R is A minus BQ. So A minus BQ minus B is greater than or equal to 0. Or you can say A minus BQ plus 1 is greater than or equal to 0. It is also a number of the type A minus BK. And every number of the type A minus BK is a member of S. So this is a member of S. So this A minus BQ plus 1 belongs to S. But what it is actually R minus B. So this means your R minus B belongs to S. And without any doubt, we know that your R is greater than R minus B. So R minus B belongs to S and R minus B is smaller than R and is greater than or equal to 0. Which is a contradiction because we have taken R to be the smallest member of the set S. And here we are having another member which is smaller than R and belongs to S. Which is a contradiction which cannot be possible because R is the smallest member of the S. How a smaller number than R can belong to S? So we arrive at a contradiction, and why this contradiction? Because we have taken R to be greater than or equal to B. So R cannot be greater than or equal to B. R must be less than B. So this part is also proved. And finally, we are just to show the uniqueness of Q and R. So we have proved that A can be expressed as BQ plus R, where R is strictly less than B and is greater than or equal to 0. Suppose, if possible, there is another set Q dash and R dash. So A is equal to BQ dash plus R dash, which also satisfies the same thing. That means 0 is less than or equal to R dash is less than B. So there are two sets. We have supposed that there are two sets satisfying the same condition, which is not possible because we have to prove that Q and R are unique. Now subtract these two. Subtracting, what you are going to get, A will be cancelled out. Here you will get B Q minus Q dash, and take this R minus R dash to the left hand side. You will get R dash minus R. R dash minus R is B times something. So this means your B divides R dash minus R. R dash minus R. R lies between 0 and B, including 0, but strictly less than B. Similarly, R dash is greater than or equal to 0 and strictly less than B. From here, you can see that your R dash minus R is strictly less than B and is strictly greater than minus B. Your R dash minus R lies strictly between minus B and B. And B divides this number. B divides a number which is strictly lying between minus B and B. And between minus B and B, there is only one integer that is divisible by B. What it is? It is 0. What it is? It is 0. Because between minus B and B, no other integer other than 0 is divisible by B. So that means this R dash minus R must be equal to 0. And it means R dash is equal to R. And if you put the value of R dash is equal to R here, what you are going to get? B into Q minus Q dash is 0. But your B is strictly greater than 0, it is not 0. What it gives? It gives Q minus Q dash is 0. So this means Q is equal to Q dash. So if you take another set Q dash and R dash satisfying A is equal to BQ dash plus R dash, with R dash lying between 0 and B, may be greater than or equal to 0 and strictly less than B, then your R comes out to be equal to R dash, Q comes out to be Q dash, proving the uniqueness of Q and R. So this set of integers Q and R is a unique set. So there is a unique solution for this equation. A is equal to BQ plus R with R greater than or equal to 0 and strictly less than B. So this is the proof of division algorithm. In the next video, we will cover more and more parts of divisibility. Till then, thank you once again.